So Barbara Terhal is from TU Delft, and she'll be speaking about scalable use and decoding of GKP qubits in circuit-QED. Oh, and I should say, before we go on, I'm sorry, I forgot. Further questions, I didn't get to all the questions in the chat, so please just copy them over to the Slack, and hopefully Akira will be able to address them there. So Barbara, the floor is yours. So it'll be a 40-minute talk. Yeah. I'll give you a warning at 35.
Yeah, good. I'll share my screen. Let's see. So you see my screen now, correct? And my cursor, good. Yeah, thanks for inviting me to give a talk at this very, very nice workshop conference. I'm not so sure that I'm very ambitious about my talk. I want to give a few comments, and these comments or thoughts basically are also expressed in this paper by myself and Jonathan Conrad and Christophe Viau about scalable bosonic quantum error correction in circuit-QED, kind of reviewing, the state of the art, including, bias noise qubits and GKP qubits, and then a few results on this earlier paper. And here you see I generated some subtitle, is analog information a feature or a bug? And maybe this goes a little bit also into the discussion of the panel that you saw last night. Should we, bosonic qubits could be interesting because they're hardware efficient, but they're also more complicated beasts. And does that provide an obstacle or more challenges if we want to use those qubits in, a further architecture using, say, the surface code? And the goal of, using GKP or other bosonic qubits is, of course, to, in a further architecture, is, of course, to bring error rates down more. Because we cannot expect that we have our final qubit when we encode our qubit in a single oscillator. Okay, yes, so let me just, okay. So one thing, so my talk will be sort of three parts. One is, like I said, it's a bit of a comments. One is just a mathematical curiosity that I want to share with you, because it is in the appendix of this review paper, and I kind of enjoyed, working on this a little bit. And the second thing is something on decoding thresholds for what we call the GKP toric code. So it's a concatenation of a GKP qubit with a toric code. So in the usual toric code, my qubits are transmon qubits or something else, and now they are GKP qubits. And the third thing is general considerations on variants of this GKP toric code and what are sort of bottlenecks. Okay, so first, the mathematical curiosity was a question that we asked. Actually, this was partially asked in the paper with Victor Albert and all. Upon dephasing, what's the or maybe you don't need to have dephasing. What is the photon number distribution in a GKP state? Now, as we know, GKP states, there are perfect states that are unphysical, so we need to have some approximate form, and there are several forms of that. And there's been a paper by a few authors, Matsuara, I have it on the next slide, and et al., that also show how these different mathematical approximations are actually all the same if you transform parameters in the right way. But for this, I'm going to, there's this one approximation, which is as follows, which involves an operator D. But let me first say, I'm not actually going to, what I'm going to say is not going to be about a GKP 0 or GKP 1. It's going to be about something called the sensor state. And the sensor state, very simply, is a +1 eigenstate of these two stabilizers. So the difference with GKP is that if I fix my two stabilizers, I still have a two-dimensional subspace that is stabilized. And if I fix these two, if I choose these two stabilizers to be this, they're still commuting. I have a single state that is stabilized, and that's the sensor state. And you see the reason to focus on this is that there actually is some mathematical result that relates to this. And that mathematical result has not been derived if I would take the GKP state. And Okay, and so you see this state has a very much symmetry between P and Q. And so if I would rotate the state by pi over 2 in phase space, it's invariant under that rotation. So it's invariant under this rotation, which means that the photon number in the state is 0 mod 4. Okay, so if we imagine that perfect state, we apply some approximating operator. In this case, this is taken to be this, and there's a parameter delta, which is called the squeezing parameter, which, you know, if this is very, very small, it goes to 0, I approximate a perfect state. And then, of course, I can look at something like this, the Fock coefficients, and what I get is something, an object like this. And this is this function. This is the Hermite function of an argument, but I sum over all arguments. And so you can ask, and what we ask, is there actually some expression for this object? Is this a known quantity? Because it's not such a simple thing. Now, because using recursion relations of Hermite functions and Hermite polynomials, you could actually plot these coefficients also over a GKP state. So that's not the question. The question is just, what is this object? And this sort of fascinating. And it turns out that quite recently, actually, this is a paper that's published in 2020, that some mathematician has derived an expression for this quantity. So in principle, C2n, the Fock coefficient, actually maybe this should be 2n here. That is equal to this, but I know that the photon number has to be 0 mod 4. So only when n is even here is this quantity non-zero. And it turns out that this quantity is equal to some function that is known. I can give you the function, but it is not so useful, times some integers, sequence of integers, which was never, this is not a known sequence of integers that people have found before. It has, blows up quite readily, as you can see, because it grows like this. And this sequence of integers shows up in the Taylor coefficients of a function, the Jacobi constant theta 3, if I expand this function around x is 1. And that is going on to this paper, and it just turns out to be that expression, exactly relates to this. And the point I want to make now is that if you, it is indeed true that if you plot the probability for the Fock state n, then you do see a thermal trend. And what I mean with a thermal trend is that an approximate GKP center state has an average number of photons. And I could look, of course, at a thermal distribution with that average number of photons, and that has a certain shape, and that's what I'm comparing this to, right? So the average number of photons will depend on the amount of squeezing that I have. So this delta parameter, and so here you see the plot for delta is 0.3. This line is the thermal distribution, and these points here are the actual value of the probability distribution. And you see that it has fluctuations. Now, of course, we're actually going out to very large n, and this is very, very small, but that's just to show the full plot. We could, of course, have focused on this thing. And the point is that these fluctuations sort of, should be revealing this underlying number theory, which is kind of a cute fact, I find. I'm not sure, there's any way of measuring this or connecting to experiment, because, the actual state you have is not of this form identically, and so, it's not necessarily useful. Okay, so that was for the mathematical curiosity. And so now let me talk about this scalable use of GKP qubits. And so I also work on sort of, doing surface code with transmon qubits. And I just want to make a few comparisons between this and what I could imagine as a scalable use of GKP qubits. So we like the surface code. There's a very good reason to like the surface code. Maybe we want to also do bias noise surface code or variance, but it's hard to beat the surface code. So in the surface code, we have our qubits on these lattice sites. And now we imagine that every one of those qubits is not a transmon qubit, but it is a microwave cavity in which I encode, say, a GKP state. And maybe there's some local infrastructure such that I stabilize this GKP state as well. And so our prescription for surface code parity checking is that we should be measuring these operators on our qubits. And so now that every qubit is a GKP qubit, we put bars on these because this barred operator should be the logical operators of my GKP qubit. And now one small comment is that if your GKP qubit is never in the perfect code space, that's never a finite, infinitely squeezed state, and these operators, if I have qubits, then of course XX and ZZ, the product of XX and ZZ commute, but this is not true for these operators. That's to say, if I look at the commutation, and if I have logical X on qubit 1 on GKP qubit 1, logical X on some GKP qubit 2, and logical Z on qubit 1, and logical Z on qubit 2. So without the inverse, this would not be 0, because these are displacements, and yeah, so these are not. Okay, so these are displacement. Yeah, so the point is that if my qubits are in the GKP subspace, they commute. But if my GKP qubit is some state in this oscillator space, these parity checks don't commute if I don't make a small change. So I should make a small change in which I, revert, instead of using logical Z, I use some Z inverse, so with a minus sign here in some of these checks. That's not a big deal. But it does point to something that actually is also occurring a little bit with regular qubits, and it actually shows that this looks sort of better in the following sense. So if I have a normal surface code with transmon qubits, one very annoying source of errors is that the transmon qubits can be in the state 2, right? They are not in the qubit subspace, but they're in the next higher level. And then if I were to do a parity check involving such a qubit, say one of the 4 qubits is in the state 2, then basically it doesn't impart the right phase on my ancilla qubit. And you could view it as that qubit that is leaked is kind of out of the stabilizer measurement. So effectively, instead of measuring, say, the parity of 4 qubits, I would be measuring the parity of 3 qubits. And the point is that parity checks which act only on this 3 qubits, they don't commute. And when they don't commute, if you measure 2 operators after each other, you get randomized values, so you don't get the right information. And so a good thing about this GKP use of GKP qubits in the surface code is that you can actually modify the surface code check such that they still commute on the full oscillator space. Okay, so that's the point I want to make. Okay, so so in principle, if my GKP qubit is in the code space, which it's never perfectly, the eigenvalues of the surface code check are again plus or minus 1. If my GKP qubit is not in the code space, the eigenvalue is a phase. And so if I were to, and this is, so the question, do I measure this surface code check in some way that I retrieve a single bit, then of course I lose some information because it's a phase. Also comes with its own error. And also the readout that you have to do, like for example, if you print this eigenvalue of the surface code check on a transmon qubit and you read out your internet connection is unstable, I read, but okay. So if you write your surface code check eigenvalue on a transmon qubit and you read out your transpon, you have lost this analog information, or you're not taking advantage of that. Okay, so now what I want to, so brings me to the second point I want to make. And this is described in this paper here below. What we do in this paper below, we kind of do an analysis of this GKP Tora code in analogy with what was done for the regular Tora code or surface code by Preskel et al., by a seminal paper by Dennis Kitaev, Landau, and Preskel. And what the authors of that paper showed, this paper is called Topological Quantum Memory, is that something that we now kind of take for granted, that if you have a surface code and let's say in every QEC cycle where you measure these checks, there is some incoming error. There's some bit flips of the qubits or phase flips. And you measure these checks with some error that, if this error rate is below some value, you are, your logical error rate of the encoded qubit goes to 1, right? So this is this famous sort of threshold result. But the way this is sort of argued, besides from numerics, is by relating it to a phase transition in a statistical physics model. And this phase transition is a phase transition related to a gauge field. And I want to say something about how this comes about without giving you all the details. But the point is that if we do such an analysis for my GKP Tora code, then this corresponding phase transition is a phase transition of a very, somewhat different model. And the gauge field, which was Z2 in the case of qubits, and it's Z2 because, well, basically every qubit can, bit flip or not. That's or phase flip, but we can treat these errors separately. That gauge field now becomes a continuous degree of freedom. And phase transitions for continuous degrees of freedom can be quite different than for a Z2 degree of freedom. And an extreme case is the following, and that is what I put on this slide. It's a bit of a caricature of what we want to do. But let's imagine that we have no GKP error correction or stabilization. What I mean by that is that what we'd like is our GKP qubit to be a qubit. We want it to sit very close, sort of, to this, subspace, like say there. How do you say? Okay, yeah. Okay, I'm not saying this so clearly, but we wanted, we're trying to qubitize the GKP qubit. And let's say we're not actually doing that stabilization. And we model that in every surface code cycle, there is an incoming error on a GKP qubit. And again, the surface code checks are measured with some error rate. Now, how do we model noise on a GKP qubit? Well, one very simple model that we've used, it's just convenient for numerics and argue about, and there's no other choice that has been made in numerics, is that, for example, if a GKP qubit undergoes an error, we draw a displacement with an amplitude drawn from some Gaussian distribution, and the standard deviation of this Gaussian determines how strong the error rate is. And so similarly, we can say if we do a surface code measurement, we can also, say we measure, well, what we measure here is actually a homodyne measurement of a variable Q or P, and there's again some Gaussian on top. And we could take these error rates to be simple. This is just for simplicity. Okay, and so what we see then is that we have, there is basically, if we have no GKP error correction or stabilization, there is no surface code threshold for any incoming error rate. And I want to, I could talk more about this, Z2 and this U1 gauge theory. But this is a plot of our paper, which is a little bit dense and has a lot of symbols that I haven't explained. But I want you to focus on what's over here and here. So on this axis, on the horizontal axis, I have a sigma, and if sigma is very large, the standard deviation is very large. It means that the incoming errors on every QEC cycle is large, the measurement error is large, and if on this axis I'm here at 0, which means that my GKP qubit is really a perfect qubit, then this line here is the usual toric code threshold. That's to say, if my sigma is low enough, I'm in some memory phase, and the point is that the green hatched region, is the below threshold memory phase, and then there is a phase transition, and that phase transition is a Z2 phase transition, and above it, my error rates are too high. Now, then you can ask how this picture gets modified when I move away to this point where this is the parameter sigma m, and sigma m in our model is indirectly is an error rate that is used in my GKP error correction, and it kind of says with how much error I learn about I learn about the value of Q or P in my GKP state, right? The idea is that in order to do error correction of GKP, Q has to be, in the multiple of square root of pi, and I learn about that Q, but I learn about that with some standard deviation sigma m. And so the point is that this limit is a little bit subtle, because the point is here that I'm going to, if you say, well, what happens here? And we actually do not fully understand this. So if sigma m is, if this is infinity, which means that there's no GKP stabilization, I'm not learning anything about this QMP, then we are clearly, we don't have a surface code threshold. But this plot is a little bit complicated in the sense that I'm taking the limit sigma goes to 0, which means that that's a limit when there's no incoming error. And so when there's no incoming error, I don't have to correct anything, right? So that's a bit of a subtle limit. This is also why this green hatched region may extend. We don't actually understand whether it extends all the way over here or not. But there are sort of points here which have not been really studied. And I would say that your GKP, okay, I could conjecture something, that the GKP stabilization should be sort of below this point. And of course, I haven't explained to you what this is. And the issue a little bit with these models is that this decoding phase transition relates to quench disordered versions of statistical physics models. And these have not been studied in detail. So we try to construct this phase diagram as a sketch based on the non-disordered versions of these models. Yeah, but the point is that we should be, we will have some, if we think about, what we expect, we'll have some finite sigma. And then the question is, are we here or are we there? This is where we want to be. And what is a little bit worrisome is that you see that if you are at some finite sigma, let's say here, and you would be okay, for your, I mean, it's not a fair comparison, but like say, if you're at this point, you would be okay if your qubit's really a qubit, but now I have some finite sigma m, and I'm here in this region, I'm not okay. It's just the shape of this boundary is not very encouraging, so to say. So it really asks, how much qubitization do you really need for my GKP qubit in order for the surface code to really help you? Okay, so that's I think what I want to say about that without going into details. So now let me give you one other thoughts which maybe are, you know, they're not sort of deep mathematics, they're just sort of ballpark estimates. So what is a disadvantage? So you could say, well, nice GKP bit, beautiful, but you know, when you make your qubit sort of encoded, the thing that we learn is that in an encoded qubit, some operations you can do quite well, but other operations all of a sudden are hard to do, like, you know, encoded T-gate or something. Whereas on a regular qubit, and by a regular qubit, I mean like a transmon qubit, a fluxonium qubit, you can do, you know, very quickly in circuit-QED, 10 nanosecond, you can do any single qubit rotation. And that's pretty powerful, right? But if I have asked to do that on my GKP qubit, do it, you know, a very short time arbitrary rotation, I cannot do this, at least in the papers by by Christopher Fluhman and Jonathan Holm, and also with the experiments at Yale by Alec Eichbusch that you heard about yesterday, and other authors. They can do a rotation on a GKP qubit using a regular qubit and some other actions. So they're not really nice to do. But then you can ask, do we really need these single qubit rotations at all? Well, we do need them if we want to use GKP qubit in some supremacy architecture, you know, something where you show some computational power. The ability to do single qubit rotation and you know, adjust the angles is actually quite powerful. But if we do error correction, maybe we don't need them. Now, another challenge or interesting sort of, you know, the next thing to do is that I think we would like to have a better way of measuring the logical Z or X. Now, again, yesterday, Alec Eichbusch talked about how this is done in the current experiment in circuit-QED. These operators are displacements, so you can use a, you know, transmon qubit controlled displacement to measure this operator, right? But the point is that on the perfect code state, these things have eigenvalue +1 or -1. So coupling to a single qubit and measuring the single qubit could, you know, give that one bit of information. But if I have an approximate state with some delta, then you can just do a very simple estimate, which we do in this paper or this review paper, that if you otherwise this circuit that couples the qubits to the GKP oscillator, if it's otherwise perfect, then you'll get an error rate. That's to say, you're in a logical 0, but the qubit tells you you're in a 1. And it's just because you have finite delta. And so, for example, for delta is 0.3, which is an often used sort of ballpark estimate, you get an error rate of 3.4. Now, that's pretty high, because if you say, well, you know, that's just because of, you know, using a single qubit. Now, you could say, well, I just repeat this measurement, and that, of course, will give you, you know, I just do sort of repetition code that give you better accuracy. But a more interesting thing, and I think there also are experiments going into this direction, is to release the GKP state from the cavity and measure I or Q after maybe there's some losses, and then determine whether, you know, your Q is closer to an even or an odd multiple square root of pi. And that's sort of a fault tolerant measurement because, you know, it's not sensitive to small shifts. But of course, you have to be careful with losses. And you can also estimate just sort of taking an approximate GKP state with some delta, one of these approximate forms, and you're applying, you know, a photon loss channel on it with some rate. And then you can estimate, you know, how this changes the expectation value for, or the probability that you measure a 0 as a 0 or 1 as a 1. And that can be small, but of course you have to deal with these losses. But this is of course interesting for creating traveling GKP states. Okay, now this is a very full slide. And so what I want to say is something that we discussed in this review, which is 3 sort of ways of using a GKP code with a surface code. Now, there of course are many more schemes, but the point is, of course, not all schemes are equally easy and nice. And I just want to point out some sort of things that some sort of bottlenecks in these things. Okay, so one thing is the first scheme is all GKP and Scilla. The second is only surface code GKP and Scilla. The third is all regular qubit and Scilla. So in this architecture, I imagine that my data qubits of my surface code are represented by GKP qubits. Of course, there are many more other choices, but okay, I'm focused on GKP qubits. Now, in principle, what we analyzed in our paper, this Villot et al. Paper, is scheme A, in the sense that we said, well, okay, I have a GKP qubit, it undergoes some error, and how do I do error correction on a GKP qubit? Now, you've seen with this, I've talked with Alex Eichbusch and the Yale group, they do a error correction of GKP qubit using a single transmon qubit. But that has some disadvantages in the sense that the transmon qubit can feed back data to your GKP and Scilla. And so that if you have a bad transmon, then that scheme is not doing so well. It's not extremely fault tolerant. So earlier, more theoretical proposals proposed something like this, where instead of having it, a qubit, you have another GKP and Scilla, and you have to do the GKP version of the controlled knot, and then you do a homodyne measurement of this GKP and Scilla. And the advantage of such a scheme in principle is that this is a measurement, a homodyne measurement Q, gives analog information. It's a lot more information than a single bit that you get by coupling a transmon qubit. But the point is that, of course, this requires another ancilla, another preparation step. Yeah, so the disadvantage of this type of scheme, so what the idea is you stabilize your GKP qubit via this thing, and then occasionally you do surface code checks involving 4 GKP qubits. And those first surface code checks also involve, like if I look at the state of the surface code and Scilla, that's also a GKP state, okay? So that scheme has a disadvantage that it has a lot of extra infrastructure for this type of GKP error correction. The other, and why is that not so nice? The point is that if you think about how quickly you measure a GKP and Scilla with low error, or how you reinitialize it, it's, several microseconds at least, versus, very much shorter times for transmon qubits. So if I, so that costs time, it's not so efficient. The other thing is something that you can observe. If you do a surface code check, for example, in this circuit, I have 4 GKP qubits, and then this is a GKP and Scilla. And I need to do Control Z and Control Z inverse. It doesn't matter that much. And these gates I can do via an interaction. This is the Control Z for 2 GKP qubits. It's generated, so these are the Q and the control and the target Q. And I can write them in terms of, sums of creation and annihilation operators. And you see it's a sum over, beam splitting and 2-mode squeezing. I have to do that simultaneously. So there are ideas of how to do that. Maybe there was even a talk about it that I missed in the middle of the night. But if I want to do a C0, I'm not seeing, one could do a C0 by doing a Hadamard, of course. And a Hadamard GKP qubit, maybe it seems like it's very easy, because a Hadamard is just a quarter cycle weighting. Basically, I have to do I have to switch P to Q and Q to P. So that's just a quarter cycle weighting of the full oscillation cycle. That sounds very easy, but if I imagine doing a surface code, I have many GKP qubits, each encoded in its own microwave cavity. And these microwave cavities, I'm not sure we can all engineer them to have exactly the same frequency. So that quarter cycle weighting is not the same time for all these, different GKP data qubits. So doing a Hadamard sounds simple, but in practice, if I have many GKP oscillators, it may be you have to be doing as a single qubit gate. And like I just said, doing single qubit gates on GKP qubits is not that easy. Okay, so now,
Barbara, if I may interrupt, just
Yes.
briefly, if there's 5 minutes left of the talk portion before
Yes,
questions.
this is I have one more slide after this. Thank you.
Perfect.
Okay, so there's two alternatives. One alternative is you say, okay, I'm going to just stabilize my GKP qubit in some way, autonomously with a transmon qubit, and I'm only keeping, for the Tor code checks, I keep a GKP ancilla. Yeah, and so there's less infrastructure because I don't need another cavity to stabilize the other cavity, and but I still have these issues. But this seems more reasonable. But then you say, well, you know, why don't you get rid of for the surface code check? Why didn't you get rid of the GKP ancilla as well? And this brings me to this point where you say, well, if I do that, I measure only, you know, this qubit. It's only now it's a qubit. And then if I say I have 4 GKP states, each with delta is 0.3 coming in, what's the probability this qubit gives me just the wrong answer based on the fact that I have finite squeezing? That's already about 12%. That's because it's a factor of 4 more than what I did before. And so that really, the fact that you're only getting 1 bit of information is paying, you know, you're paying for this. And that's my point, is that to stabilize GKP, you need to get sort of analog information, and getting analog and so you can't kind of shortcut this by saying, oh, now I use a transmon qubit to control everything. But then if you get 1 bit at a time, you know, okay, then you have to, you know, do it multiple times to get multiple bits. Okay, now one last comment. I know these are sort of more discussion points that I'm talking about. When I started thinking about this, I said, wait, why are we actually doing a GKP qubit in a microwave cavity when this microwave cavity is very good? Can't we just use Fock states? Like, why would we make it so complicated? And actually, it's not so crazy. Usually people say, well, Fock states, you can't do the Hadamard, or, you know, why would you, you know, you can't always drive when you drive it to higher levels. And maybe that's true because, you know, you're more likely to leak. But you can observe, for example, that the control Z, if I have a transmon qubit to measure, you know, to measure Z checks, I need a control Z. That's relatively easy. Of course, I would like to make this tunable. But then to do the XX check, I would need to do this Hadamard. And now, if you believe the Yale group, they say, well, we can manipulate, we can implement any unitary on, you know, on some microwave cavities. So they could also rotate a Fock qubit to the, you know, they could also do a Hadamard on a Fock qubit. Yeah, so that's sort of, I think we should not sort of stare too much and saying, well, the GKP qubit, we need to make complicated states. Maybe using Fock states in the surface code is not at all a bad idea. Anyhow, so I'm done now. And to me, some of the, you know, progress in GKP qubit is really on what's happening in experiments, and I'm interested to watch out for that. Theory analysis, I do think we should do more analysis on how accurately we could do, say, a control Z gates between 2 GKP qubits from a purely theoretical consideration. Okay, but let me stop here.
All right, excellent. So that was a minute and a half early. Thank you. Let's give some virtual claps here. So thank you very much, Barbara. So we have some questions coming in. We have one question already, and as I speak and waste some time, you can add some other questions to the chat if you'd like, but I'll start with a question from Arne Grimsmo. Arne says, I just want to make sure I understand the homodyne measurement argument right. Were you saying that just because the intrinsic measurement error for delta equals 0.3 is larger than the quote measurement error due to loss of 10%, we don't need to worry so much about the imperfect measurement?
Okay, maybe I don't fully, just have to go back. Are you talking about, I'm not sure I understand this. Is it
maybe Arne can just say it.
It was that slide. I just wasn't sure if I understood what was the upshot there, kind of.
Okay, well, okay, so the upshots, the point is that I worry that if you get 1 bit information, you get that bit, because finite delta, you get that bit with high error rate. And you'd like to get more bits of information. So either you repeat your transform measurement several times, but you know, your transform is measured via a readout cavity. That also takes time, right? You cannot. So then the alternative, you say, well, I release my GKP state from the cavity. But then, of course, the point is that now the state is gone. I have to reinitialize it. That has that disadvantage. And then you do have to, you know, consider like what losses do you incur when you release it. And it really just depends on the loss error rate, what the error rate then is on the final measurement. So the point is this number here that I put here, Q is 0.5, that just comes out of an analysis that I apply a GKP 0 or 1. I apply the, you know, the photon loss on it. And then I look at whether the probability that Q is closer to an even or an odd multiple of square root of pi, you know, that kind of analysis. Does that answer your question?
Yeah, I think so. And I mean, the other thing I mentioned was that 0.5 is smaller than the 3.4, which is just the like intrinsic error for having an approximate state. So,
well,
so
the
like
point is that so delta is the same here in those cases. So I took a delta, which is your GKP approximation, and then I say, due to that delta, you know, what's the error that I'm getting? If I just, you know, I have that state and I have a circuit with an ancilla in plus and then control Z and then measure ancilla perfectly, and then what's my error? You know, then the ancilla flips with some probability.
Okay, all right, I get it.
Yeah. Okay. Thanks.
All right, so we have another question from Christian Sigele. Apologize if that's wrong. How much does an imperfect quality ancilla GKP affect the target GKP? Put simply, can you make the target much better than the ancilla given finite squeeze states and homodyne measurement efficiency?
Well, yeah, there is a, you know, these types of circuits for, and I think this type of analysis may have, or no, this is not the circuit I want to look at. Wait a moment. Okay, sorry, it's this one. There is, if you look at the circuit, so there are two types of shifts, right? Shifts in P and Q. And so if you're, and I don't remember this exactly, but okay, so one shift, if we look at the ancilla, one shift determines the error on this measurement. The other shift feeds back to the data, right? So and that's sort of two quadratures. So if your ancilla is very squeezed in one direction so that it feeds back very little, then, or if it just is, then, you know, then you have to look at the shift in the other direction, you know, that influences the measurement outcome. So if you want to reduce feedback, then you would like to, you know, make it very squeezed in one direction. But of course, you'd like to also get this measurement right. So, so you'd like to be, you know, you'd like it to be better, indeed, in principle, than this guy. That would always be better. But of course, if it's worse, if the state is worse, then indeed it feeds back to the data. I just hope that answers the question.
Corrupts it, yeah. Well, it's 8:29. I think, yeah, I think we'll stop there. And we'll take further questions onto the Slack. And so that'll give the next speaker some time to set up. So let's thank Barbara one more time. So thanks very much, Barbara.
Yeah, sure.
Yeah, that was great. The final speaker is for this session is Jonathan Holm from ETH Zurich, and the talk title is Error Correction of a GKP Trapped Ion Logical Qubit by Autonomous Dissipation. Jonathan, floor is yours.
Good. So you can see my slides, okay? Yep.
Yes. And the pointer, yes.
Yes. I always use this one instead of the laser pointer because the laser pointer seems slow usually. Yeah. Good. Okay, so it's a pleasure to be here. Of course, it would probably be more of a pleasure to be in Byron Bay talking to you all in person, but it's great to have actually these talks throughout the day. I spent my evening listening to them while working on my lecture last night, and that was a lot of fun. So thanks to the organizers for having me included in this talk, and I've greatly enjoyed what I've seen so far. Yeah. So the aim of today's talk then is indeed, and I see I've missed a space in the title, to tell you about recent work we've been doing in the lab with our trapped ion system on error correction of a logical GKP qubit by autonomous dissipation. So the way we got into this game was we were playing with squeeze states essentially, and one of our key techniques is what have been called conditional displacements last night in a few talks. And we realized then in 2018, I was sitting in a talk of Barbara's actually, and I realized that this set of techniques was nice for preparing GKP states. And so then in a paper back in 2019 with Christoph Luhmann, then we demonstrated that we could create GKP states and perform universal control essentially on these states. And at the time, I had no real idea how we could do quantum error correction. And so today I'm happy then that we've been able to resolve that, in part inspired by the beautiful work from Yale by Philippe and Michel Devereaux's group. And that's allowed us now to see how to do quantum error correction, and that's the results that I want to present to you today. So first, I should just thank our sponsors, I think primarily the Swiss National Science Foundation for this particular track of work.